On this bell work, two problems, just basic solving equation strategies, because we're going to see some of it today. So using principles of equality to solve, remember principle of equality just says if you do it to one side, you got to do the other side, that's all. So you get this answer, W is 2, and then 2 has no solutions. You'll see the z's would cancel out completely, but it'll still equal a number. If it equaled 0, then it'd be infinite solutions. Here's our two objectives for the day. I can find the missing side length of right triangles with the Pythagorean theorem. And then the second one, I can determine if 3 lengths would make a right triangle. Take 1 minute and copy these down, please. Just a little background on the Pythagorean theorem. So, Pythagorean theorem, the name at least comes from ancient Greece, where there was a dude named Pythagoras. Now, Pythagoras was kind of like, he was a big-time nerd back in those days, or at least I think we would think so. But back in the day of ancient Greece, big-time nerds were considered quite influential, actually. But in any case, in those days, of course, they didn't have iPads and Xboxes and things like that. So what did they do on weekends? They did some math. So they'd get together with some buddies and pals, and they would do math. And people loved it. In fact, they loved it so much that the group started to expand and grow. And eventually, like just driving down the street, you'd see, oh, there's on lampposts and light posts, you'd see posters for math meetings where they'd get together and they'd do the Pythagorean theorem. And it was so great. I mean, you can imagine the type of party that we're talking about here. So, you know, like here we have like chips and dip perhaps when you get together and maybe watch football or rugby. Back in those days, they would cut sandwiches into triangle-shaped, right triangles, and then they would use the Pythagorean theorem. And I mean, we're talking till all hours of the night, these people were partying. Well, Pythagoras, of course, being the chief nerd of the time, eventually, you know, not everyone agrees with big groups, no matter how big or influential they may become. Someone disagreed with Pythagoras and called him out on it. And when you have lots of power like that and you have lots of people following you, naturally the thing to do with people that try to question you is to kill them, which Pythagoras did. So this person was like, hey, you gotta think about this a little bit more because I think you're wrong. And he says, all right, I'm going to choke you out and put you in the water. And so he did, and the guy died. And I don't know if like math nerds bury people like that or what, but I mean they buried him in water, I guess, because he drowned the crap out of the dude. But in any case, that is Pythagoras in a nutshell. Oh, and by the way, history shows that the person that called him out was actually correct. So he killed the dude for being right. Now, the Pythagorean theorem, though, it actually goes further back than the ancient Greeks into ancient Egypt. We have actual evidence of them using the Pythagorean theorem. And I also assume that everything that I just said you don't care about. What is the Pythagorean theorem? Other than something that can be kind of difficult to get used to saying or spelling. But I did use spell check on that one. Again, it has to do with right triangles like we saw in the objective. Okay? So let's look at a right triangle. And yes, we're going to assume that all my lines are straight. So there's a line and there's a line. Now these two lines, we've talked about angles before, which is good because remember, it's a right triangle. This is what we call a right angle. And we've seen the symbol before to indicate that this angle itself is 90 degrees. Okay, so a right triangle will have one angle that is 90 degrees. And then you have a side that connects the ends of the 2 points right there to make a triangle. The other two angles we don't care about yet, although later on you will. Now this is a right triangle. And there's parts of this right triangle that we need to be aware of because it's vocabulary stuff. For example, this red side length here on the left is what we call a leg. But the purple side is what we call a leg. Now, those are the same word we use for legs. Those two sides, the legs, make up the right angle, right? Purple and the red make up the right angle, okay? It's important that you understand that. Why do they call it a leg? I don't know. Someone a long time ago, way before I was born, made that up, okay? So I have no control over it, but that's just what they call it, so that's what I call it as well. Perhaps that's a form of brainwashing, but either way. Okay, so the two legs make up the right angle. The side length that does not make the right angle, because there's only three sides, is what we call the hypotenuse. This is how I think you spell hypotenuse anyways.
I like legs better.
This should be like
Now, while you may not prefer or like the word hypotenuse, just think about this, okay? If you're ever in a discussion with your friends and you just throw this out, they'll be like, "Well, look how smart you is," okay? And you'll be like, "Holy crap, yeah, wow." They think I'm so smart, whether you know what it is or not, doesn't matter. But if you use the word hypotenuse in your everyday discussions, people will stop talking to you and they'll be like, "Look at the nerd," okay? Now, if that's what you want, then do it all the time. If you don't, then don't use it. Okay. However, in this class, of course, we're going to use it because, well, it's kind of a nerdy class, and yes, I'm a nerd as well. Now, let's be clear on this. I don't really care what the crap you call it, but these are the vocabulary words I'm going to be using. So if you call it something else, just know that you may get a little more confused than you need to be on these, okay? Now, the Pythagorean theorem. Well, it has to do with right triangles like this, particularly the side lengths, and of course the one angle has to be 90 degrees. But the Pythagorean theorem is a conditional statement, meaning it's an if-then statement, okay? If something, then something else. Well, what is the if-then statement? Let's find out, okay? So it would start as, of course, it has a right triangle. If you have a right triangle, see if I can fit this in there. If you have a right triangle, see how I fit that word in there? Then what happens is if you take the leg, if you take one of the legs and the other legs, let's say that you made squares out of these and added those two areas together, it would be the same as taking the hypotenuse, which I believe to have spelled correctly, but I also believe that I could have made a mistake there, as a square. All right, so those are powers of 2 when I say squared, by the way. So if we wanted to just write this in a more simplified form, the legs are referred to as A and B, and the hypotenuse is referred to as C. But and this is, you'll hear this from time to time if people want to show how nerdy they are. They'll say a squared plus b squared equals c squared. Almost like they found equals mc squared. I don't know. But people use this all the time. Maybe it's the exponents that make people go crazy over this. I don't know. But they love it. All right. And this is the Pythagorean theorem. Now this is very specific. You have to have a right triangle, right? There's lots of different types of triangles, but right here we're just talking specifically about right triangles. Now right triangles used a lot, just like, of course, they did in ancient Egypt and Greece, and since then, which is, well, I mean it's useful, but actually the Pythagorean theorem has lots and lots of uses. You'll see this in physics with like force. Engineering uses this quite a bit as well. All right, so we're going to be using this formula throughout this lesson. So I'm going to take this and copy it, and we'll set this aside here, okay? So this goes way back. This is called the windmill proof of the Pythagorean theorem, and this is showing just what I was telling you guys. If you take the two legs, which is A and B, and you made squares out of those legs, like I'm showing you right here, then if you took the square of the hypotenuse, like this, then you would be able to fit both of these areas into this area right here. That's pretty much what the Pythagorean theorem tells us. Now, I'm not going to show you that explicitly today, but you're welcome to go home and make yourself a right triangle and then cut it out with scissors, and then you can fit those two squares into the hypotenuse square. So remember, these are like squares, and what we really want is the square root, because we just want the side length on these squares, not the actual area. But the area should help us, now that we have roots, to find the length of the squares. Now, there's our Pythagorean theorem. And I got two legs, right? The legs make up the right angle, so there's our first leg at 9. And then the second leg here is 12. Now, does it matter which leg is which? No, it does not. Perhaps that's why they made the same name, but I don't know what they call legs. But yeah, if you put the 12 here and the 9 here, it's not going to matter. But here's what I do know from the Pythagorean theorem. If I squared both of those and then added the results, I would have the hypotenuse, which is shown as c, to the power of 2. All right, so it's like a formula like we were dealing with in volume or surface area. You're just plugging in values into this formula and then solving for whatever value is missing. So I would put in the calculator 9 to the power of 2 is 81. 12 to the power of 2, 12 times 12 is 144. If I add these together, I should get the hypotenuse to the power of 2. And when I add these together, 81 plus 144, and a 5 and a 2, 225. All right, and this is all hypotenuse to the power of 2. Well, we don't want hypotenuse to the power of 2. We just would like the hypotenuse, c. So, to undo an exponent, we use roots. In this particular case, a square root. But the principle of equality says if I do it to one side, I must do it to the other side. And the square root of 225 in the calculator, I push some buttons, I get 15. Boom. So this hypotenuse length would be 15. Let's solve for this hypotenuse with the Pythagorean theorem. All right, so here's my first leg. Again, it doesn't matter which one you say is first or second. But that leg I'm trying to color code these, by the way, is 2. The second leg that makes the right angle, 6. So our unknown is the hypotenuse. So let's square the legs and find the sum, which should equal the hypotenuse to the power of 2. So in my calculator, 2 to the power of 2, actually I just did that in my head, but 2 times 2 is 4. We should have that down pretty quick. 6 to the power of 2, 6 times 6 is 36. So I'm going to add these together. It should be the hypotenuse to the power of 2. Well, adding these together, 4 plus 36, I get 40, which is the hypotenuse to the power of 2. Well, I don't want the hypotenuse to the power of 2. What I would really like is just the hypotenuse. So to do that, we'll have to square root not only the c to the power of 2, but the other side, right? Principles of equality, square root of 40. So I plug this into the calculator, and it gives me 2 times the square root of 10. Now again, going back, this is what we call an exact answer, because it's not showing a decimal. But what we really want, even on the assignment, is an approximation. All right? So remember, once you get 2 times the square root of 10 in your calculator, just push the double arrow button that's right directly above the enter button. And let's see, I don't know that is my head, but let's find out. 2 times the square root of 10, enter. All right, gotta push the double arrow button. 6.32455532. I'm gonna round this to the nearest thousandth, although I think on the assignment it wants you round to the nearest tenth. So 6.3245 would make that 325. Now there's no units on this because they didn't give us any units, but you'd want to label that if it did. Also, keep in mind that now that we've seen this with triangles, on the assignment there are some questions that they will not give you the triangle, okay? So, but it'll say, here's the leg and here's the leg, find the hypotenuse, and then, I mean, you can always draw your own triangle if you need to. All right, here's another one, and again, they've given us a leg and a leg. Now, the first leg I have there in red is 5, and the second leg I have there is the square root of 11, all right? The hypotenuse we do not know, but we can solve for it with the Pythagorean theorem. So square the 2 legs, add that together, and it's the hypotenuse squared as well. Now that square root of 11, I would put that in parentheses, more for future reference, okay? Again, that kind of has to do with the program of the calculator, because later on, I mean, that would work no matter how you plug that in pretty much into the calculator, but later on it will not, so be careful. So I would put this in the calculator, right? 5 to the power of 2 is 25. And remember, squares, powers of 2, and square roots pretty much undo each other. So on that, I should get 11, no matter if you put that in the calculator or not. And the sooner you realize that roots and exponents undo each other, you'll see that this becomes a pretty quick calculation right there. So now we're ready to add these 2 values together. 25 plus 11, boom, 36. And this equals c to the power of 2, or hypotenuse to the power of 2.
And that's easy to do in your head.
Yeah, we should be able to do that in our head. So I'm going to square root that, though. So So even if you need a calculator though, you should still get the same answer of 6. So the hypotenuse in this case would have been 6. So on this one, we're trying to find a leg, which hopefully is not too bad right there. And there's our Pythagorean theorem. So I'll say the red here is the first leg at 0.12. The second leg, of course, is unknown. And it's okay if a leg is unknown. We can solve these if a leg is unknown with our principles of equality. And then the hypotenuse here shows at 0.2. Well, Pythagorean theorem says take the two legs, square them individually, add those values, and it's the same as the hypotenuse to the power of 2. So in my calculator, I put these in. And let's see, 0.12 to the power of 2, 0.0144. Of course, we'll add b to the power of 2. But we can put 0.2 into the calculator as well, which is 0.04. All right. Now, this is an equation that I need to solve for b, so I don't want that 0.0144 added to it. So I'm going to subtract it from both sides. Subtract 0.144. Why? To zero that out. But again, if I do it to one side, I must do it to the other side as well. 0.144. So if you need the zeros right there, that's fine. I'm actually just going to put it in the calculator. So I have the leg b to the power of 2 equals, let's go and see what we get here. 0.04 minus 0.144.
0.0144.
Yeah, I put it in on 0.0. Oh, I'm working. 144. Enter. And I get 0.0256. All right, now I don't want b to the power of 2, though. That's the area. I want the length of that square, so I'm going to square root that area. Which leaves me with b, just the side length of the square. Oh, I should put it in the calculator, shouldn't I? It appears that it should be 256. I'm looking on the poster. 256. I see that's 16, so it should be 0.16. But let's put it in the calculator just to make sure. Yep, 0.16. 0.16, and that would be the length of that leg. All right, more Pythagorean theorem stuff. Leg squared plus leg squared is the hypotenuse squared. And we got the a right here, which is a leg, right? Because it makes up that right angle. The other leg is 4. And the hypotenuse we know is the square root of 41. So the Pythagorean theorem says square the legs, add that together, and it should equal the hypotenuse to the power of 2. And if you're going to put that in the calculator, just use parentheses. And again, we'll see a problem later on that will pretty much require the parentheses. So a to the power of 2, nothing to do there. It's just a to the power of 2 plus 4 to the power of 2, which is 16. This equals square root of 41 to the power of 2. Again, that just brings out the 41 from the square root. Okay? Now in solving this one, I'd say, well, subtract 16 from both sides to zero that out. So you're left with this a to the power of 2 on the left, which equals now 25. And we've seen that one before, just square root, we know the square root of 25, hopefully is by now 5. So that's the side length, the leg of this right triangle is 5. Here's our Pythagorean theorem. And once again, they've given us a leg at 10, another leg at x, that's okay if it is, by the way, and then the hypotenuse, 10 times the square root of 2. All right, now the Pythagorean theorem says take the two legs, square those, take the sum, and it should be the hypotenuse to the power of 2. Now this is where we definitely need the base 10 times the square root of 2 in parentheses with the exponent outside the parentheses, okay? Especially if we're using a calculator to plug this in. So 10 times 10, of course, we know is 100. But 10 times the square root of 2 to the power of 2, in parentheses, by the way, that should give us 200 right here, okay? So if I add those together, the legs squared, of course, I got x to the power of 2 still, equals 200. I just got to solve this like I would an equation. So let's zero out the 100 by subtracting it from both sides, zeroing it out. So I still have x to the power of 2 equals now 100. But I don't want x to the power of 2, I just want x, right? Just finding the value of x. So undo the exponent with the square root, which gives me just x. The square root of 100 is 10. Boom. Now we're going to use the Pythagorean theorem to solve it. That should be pretty well expected by this point in the lesson. So there's the Pythagorean theorem. Let's look at the two legs. X right here. So there's our first leg is x. And the second leg is, well, x. The hypotenuse is given as 20. That's good. Thank you for the hypotenuse. But we got the two legs. If we square those and add them together, we're going to get the hypotenuse to the power of 2. Now for me, I already know 20 to the power of 2 because I put in the calculator already, but it's 400. So as of right now, before I look at these with colors, just look here, okay? Well, actually, let's look at them with colors first. The red leg and the purple leg to the power of 2 added together. Now what we notice, though, is that the two legs have the same base, x. Okay, now this goes way back into, I think, Unit 3, where if you have the same, well, pretty much the same base and the same exponents, then we can treat these as though they are like terms. And the coefficients are phantom values right now, 1s, okay? So if I looked to combine these, which I am, how many x to the powers of 2's would I had? 2 of them. 2 times x to the power of 2 equals now 400. And hopefully you can kind of see what's happening here. To solve this, we'll divide both sides by 2, which leaves us with x to the power of 2 equals 200. Now that's one of the side lengths, and remember, we're only looking for the value of x here. And x to the power of 2 is that. So I'll have to square root both of those to get just x. So x equals the square root of 200, which is 10 times the square root of 2. I think we've seen that value already, but just to make sure, I'm going to put it in my calculator. 10 times the square root of 2. Of course, it gives me 10 times the square root of 2. Double arrow button, and I get, again, this is more an approximation. X equals 14.1421356. I'll round it to the nearest thousand. 142. Either one of these will work. All right, here we go. Megan did this work and she made a mistake. This is a more common mistake than we like to see. But it says, hey, look, you got a leg here, and this is the hypotenuse, but we see that this hypotenuse she replaced into the legs. So the setup is correct, it's just she misplaced one of the values. So the 13 should have been right here. If you solve this where the b is the unknown and the c value is 13, the hypotenuse, then eventually you wouldn't get this stuff, but you'd find that c is 12. Well, how do I know that? It's because this is what we call a 5, 12, 13 right triangle, which is also known as a Pythagorean triple. So Pythagorean triples have only whole values, such as these, 5, 12, and 13, but the three side lengths make up a right triangle. And so another one, which we've seen, is 3, 4, 5. Maybe I'm thinking of a different class, but 3, 4, 5 would work. And these are scalable, by the way, which is nice. Okay, of course, there's many others, but these are two very, very basic ones that are used. A 3, 4, 5 triangle is used a lot in construction to ensure that walls are what they call square or 90-degree angles. So what you would do is you'd make a square like this. You'd say mark here is 3 inches, and then mark there is 4 inches, and then if you find that this length is like 5.5, then you know it's not a square. It's not a right angle. Okay, what happened on this one? Raphael says the side lengths are 4 and 5, the legs, that is. So this is a good setup. 4 to the power of 2 plus 5 to the power of 2 is c to the power of 2. So on this one, right, 16 plus 25 is 41, but notice that somehow this exponent has disappeared. So that'd be c to the power of 2. So if you wanted c, of course, you just square root both of those. So c would be the square root of 41. That's simplified. I don't know what the decimal is, and I don't care, but this is the mistake that was made. Okay, just make sure that you keep the exponents until they're rooted out. Like a den of vipers. The converse of the Pythagorean theorem. Let's look at the Pythagorean theorem first. All right, there's the Pythagorean theorem at the bottom, right? Now that's an if-then statement, which is important to know. So the converse is where we just take the if-then statements and just reverse them. So over here, it's still an if-then statement, okay? But the if statement becomes the then statement, and the then statement becomes the if statement. So here's what I mean. So if you have a leg plus a leg to the power of 2, the squares of the legs, added together, if that equals the hypotenuse to the power of 2, then as it turns out, you would have a right triangle. Boom. There is the converse. So a converse just means we're kind of flipping the if-then statements. It's still an if-then statement, but we're reversing where the statements are. Okay? So what this means is that they're going to give us 3 lengths, and we're going to put them into the Pythagorean theorem. If it comes out as true, then we know that we would be dealing with 3 side lengths that make a right triangle. Be careful, because on these questions, when they give you 3 values, they're not always in order from least to greatest, or greatest to least, by the way. But one thing you need to understand is that for a right triangle, like we see down here, the hypotenuse is always the longest or the biggest of the 3 sides. So if they give you 3 side lengths, and you're not sure which is which, always know that the biggest of the 3 is the hypotenuse. Well, what if they're all 3 the same? Then it doesn't matter which one you put as the hypotenuse or legs. Of course, that's an equilateral triangle, but not that we care about that, okay? But for the 3 side lengths, and again, it's not always going to be in order. They may say, well, it's 1, 54, and I don't know, 6, like this, right? That's not in order, obviously. And we should know, by the way, that this does not make a triangle because of what we've talked about before. Remember, the 2 smaller side lengths have to add up to be bigger than the biggest side length as well. Here's our first example. Okay, and these are listed in order. That's good. So the 2 short sides, right, are the legs. There's our first leg as 11. Second leg is 60. And remember, the biggest side has to be the hypotenuse. That's a 61 right there. So we're going to square the 2 legs, add those together, and that should equal the hypotenuse squared as well. All right, so 11 to the power of 2, boom, 121. 60 to the power of 2, 3,600. 61 to the power of 2, 61 to the power of 2, enter 3,721. 3. Now, when I add the 2 legs together, it should be the same as the hypotenuse. So I should probably go back and let's put a question mark above that equal sign, because I don't know if this is true or not. But when I add these together, 121 plus 3,600, I get 3,721. Does that equal 3,721? Well, they're not the same color. Doesn't matter. We're looking at value here. And yeah, these are the same. This is a true statement. Since that is true, yes, these 3 side lengths would make up a right triangle. All right, let's see if this one fits the Pythagorean theorem. Again, we're just seeing if it makes a right triangle. Okay, so my first leg here is 2. My second leg is 4. My hypotenuse is 6. Well, if I square the 2 legs and add those, it should be the hypotenuse to the power of 2. But we don't know if it is, so I got a question mark above the equal sign. 2 to the power of 2 is 4. 4 to the power of 2 is 16. Oh, we know the C value. What am I doing? That's 6 right there. 6 to the power of 2 is 36. Now, I'm going to finish this, although not everyone would need to at this point. But I know 4 plus 16 is 20. Does this equal 32? Not last time I checked. I mean, things may have changed. 36, yeah. See what happens when you get going too fast. 36, thank you.
Why is it true?
Because I wrote it wrong, obviously. It's false. Yeah, false. Well, that's clearly not true. It's false. Maybe I should have put not true. I guess it's the same thing. Yeah, this is clearly false. 20 does not equal 36, at least yet. So, I know, the times are changing. But in any case, that means that if we go back to the original question, the side lengths given below satisfy the Pythagorean theorem. It's just asking, does that make a right triangle? No, it does not. Now, some of you didn't even need to go that far, by the way. Like, all of this stuff was unnecessary because, like I said before, we've seen this. 2 plus 4 is 6. Remember, the two short sides have to be greater than the longest side. So there actually wasn't really need to check if you remember that from way back.